Thanks for this very this invitation to this prestigious venue. I'm very happy to be here. So, as Xavier said, I'm Stanley Durrleman, and I'm in the RMS lab, which is a joint team between INRIA, the National French Institute for Applied Math and Computer Science, and the Brain and Spine Institute, which is a neuroscience institute located within a Pitié-Salpêtrière hospital in Paris. And I think that the presentation will reflect this dual interest in both applied math and computer science on the one hand, and neuroscience on the other hand. Actually, the driving motivation of the work of my lab is mostly Alzheimer's disease. So in 2 words, Alzheimer's disease is a very complex disease where it starts by the accumulation and propagation of lesions in the brain, which has multiple effects on the brain anatomy, function, and metabolism, which at the end has as consequence the onset of symptoms. And when these symptoms are manifest enough, you are diagnosed with the disease and you start being taken care of. Okay, the whole problem is that all treatment have been tried on this latest phase of the disease, and they haven't been shown to be effective. Also, they have been shown to be effective to clear some of the lesion that occurs years before. So the whole game now is to refocus the interest on the disease and this, what we call the preclinical stage of the disease. But this raises difficult questions because, of course, in absence of symptoms, this phase is particularly difficult to observe, and it's particularly complex. So we want to address that in a statistical learning way, where we propose to build what we call a digital model of brain aging during the disease progression. And by informing this model with all the data that are available, which informs us about all these consequences of the disease on the different aspects of the brain. And these, so to have very 2 clear goals in mind. First is to much better understand this preclinical phase of the disease, and to be able to predict when you will develop a particular symptoms. So at which stage of the disease a subject might be. So, yeah, just in a simple manner, we followed subjects at multiple time points during mostly clinical research protocols. So we have different subjects that are observed during at least a few years. So just offer us a small window of observation. So they're all at different stages, and we follow them for a short period of time. And all the purpose here is to find a way to recombine all this data to be able to construct a long-term scenario of disease progression across all the disease stages, by somehow discounting all the differences across individuals. And once we can do that, we would like to be able to personalize this model to a new individual, to be able to predict what will happen in the future, in the way we can translate the knowledge of one subject to another subject and to predict its future evolution. So this falls naturally in the framework of longitudinal data analysis, where longitudinal just means multiple subjects observed at multiple time points. So the question is, how can we average these trajectories to get an average of all these trajectories? So if you look at the literature, most of the time the assumption is made that you have a good temporal marker of the progression of the phenomenon that you are observing. So for instance, in a pharmacodynamic modeling, you know when you inject the drug. That's the starting point. And if you have such markers, then the whole story becomes more or less a question of regression. How can you analyze the variability of across the subject for the subject as the same markers, the same stage of progression? And this had been proposed quite a while ago by notably Laird and Ware in 1982, and has developed in a very a large body of work. And the main difficulty here is that we don't have such a marker. We don't know when the disease starts, of course. So it's precisely the question that we have is to be able to know or to predict the stage at which a given patient is. So we don't have enough markers. So we cannot deal with that problem in the framework of regression. And what we have to learn is really distribution of spatio-temporal trajectories. So we need to find also the temporal correspondences across the different trajectories before comparing the values of the different subjects. And that, of course, raises a very difficult questions, because if you have just two data, you don't know whether it's the same person at two different stages or if these two different individuals at the same stages. So we need to disentangle the different sources of variability that we can observe in the data, in the different trajectories, direction of the trajectories, and the pace at which the trajectories are followed. And another difference is that most of the work developed in the biostatistic community is for vector valued data, so a set of biomarkers, basically. And here we want to address a more complex question. We want to inform our model with images, with shapes, with functional signals, which take the form of structured data, and this naturally is encoded into manifold valued data. So the first contribution that we made to address this question is to propose a new mixed effect models for longitudinal manifold valued data. So as a mixed effect, it has a hierarchical structure. So we assume that we have an average trajectory, which will be supposed to be a geodesic on some Riemannian manifold. From this average, we could derive individual trajectories by spatio-temporally transform this average trajectories, that I will explain later how we can do that. And then we see the observation as noisy samples along these trajectories. So the key aspect of this method is the way we will define the spatio-temporal transformation. And for that, we propose the concept of X-parallelization to be able to extend the concept of parallel curves on a manifold. So here you have very schematic manifold, and there is some specific point P0 here, and you have the tangent space and the velocity vector. And we take a vector here, which is in the same tangent space at P0. And then we propose to parallel transport this vector along the curve and to exponentiate this parallel translation of the vector on the manifold and to give a new point. And if you repeat this process, then at the end you build a new curve on the manifold, which in some sense is parallel to this reference geodesic. And on the sphere, it's really like what we call a parallel on a sphere. So now we can explain the whole hierarchical model, statistical model. So points are, observation are seen as points on the manifold, high dimensional manifold, but still a manifold. So we assume the average trajectory to be a geodesic on this manifold, which is parameterized by a specific point, a velocity, and a time t0. Then, to derive a specific individual, we have an individual effect, which is a velocity here, which is chosen to be orthogonal to v0. And we define the parallel curve, the x-parallel curve on the manifold to be the average, the individual trajectories for a specific individual, and you can repeat that for different individuals. And then we combine this parallel by time reparameterization functions, because there is no reason for one subject to evolve at the same pace as another one or as the average. So we account for these differences, dynamic differences, by time reparameterization function, which is typically an affine transform. And so at the end, we see the samples as noisy samples along these individual specific trajectories. So this model allows to the estimation of both fixed effect or population average trajectories and individual effects, which are the parameters of this spatial temporal transformation of the trajectories. Here we have an orthogonality condition here, which ensures a unique space-time decomposition. If we have a component of Vi which is parallel to V0, then this will play exactly the same role as the time parameterization function. So that this orthogonality condition, which allows us to disentangle what we call the spatial variability, which means more the difference that you see in data from different individuals, and the time variability, which is more the variability in the timing and the relative timing between the different events on a specific trajectories. And so in this framework, you see that time is no more considered as a covariate, but really included as a random effect in the model. So to summarize the random effects, we have these acceleration factors here, which allows to adjust the pace of progression. We have a time shift here, which allows to shift the trajectories ahead or in time. And we have this Vi. So the Vi is in the orthogonal of V0 in the tangent space, so it might be very highly dimensional. If we are in very high dimensional, it's n-1 dimension. So we propose in the spirit of independent component analysis to see these vectors as a random superimposition of independent components, where now we have the components are encoded into the columns of a matrix A, and the sources here are random variables. And the fixed effects, which are the parameters of these average trajectories, so a point, a time, and a velocity. So then we can just abstract this model as any statistical model, as we have observation. We have all the random variables that are into a single vector Z, which so as the VI's, the acceleration factors, and tau i's. So we have time shift, space shift, and acceleration factors in those random effects Z. And we have a number of parameters, which basically are the parameters of the population average trajectories plus some variance parameters. And then all the question, of course, becomes how can you estimate the parameters given the data? So there are multiple choices of algorithm for doing so, but here we have very highly nonlinear settings, so there are not so many choices actually to make inference in this setting. And we at the moment we're stick with this MCMC AEM approach that I will describe here a bit more. So all the goal is to find, I just don't assume prior for the sake of simplicity. So we want to optimize the likelihood of the observation given the parameters, which requires to quotient out all the random effects Z. Now, of course, this is completely untractable. We don't know how to compute this integral. So we rely on a very famous approximation scheme, which is the expectation maximization scheme, which tells you that you can optimize this by a sequence of approximation where at each step k plus 1 of the algorithm, you optimize this function, which is so the expectation of this log complete likelihood under the posterior distribution. And in there you have the theta here is the value of the parameters of the previous iteration, and this theta here is the variable over which you have to optimize. So there are good and bad news here. So the good news is that this complete likelihood here is known usually, because this is likelihood is given by your model, and this is given by your priors. So here usually you know that, but for a specific theta. But here you don't have a specific theta, you have generic theta. You have the posterior here. The posterior is quite difficult because you don't know how to sample from this distribution. You know it only up to a normalizing constant. And you have the maximum, and of course you don't know how to maximize this. So we can address this in 3 different steps. So the first step is to assume that this complete likelihood here has quite a specific form, and we can show that actually we can always make a trick to end up in this, having a distribution of this form, where you separate a function of the parameters with function of the observation and random variables. And this has great advantage because now you can put this, this function of theta outside of the integral. So the maximization process now is very easy because you know, if you know what is inside this big thing here, you know how to maximize over theta. But of course, now the problem is you don't know how to compute this. Two problems, the integral here and the posterior distribution there. So the integral is simply can be approximated by a Monte Carlo sequence. And so here the people propose to have a Monte Carlo simulation by updating, by sampling a random variable from this posterior and to keep updating the value of this S, which is called the sufficient statistics. But then the last problem becomes that you don't know how to sample from this posterior distribution. As I said, you don't know it only up to a normalizing constant. And for this, you can think of replacing sampling from this distribution by sampling from a Markov chain, which stationary distribution is the posterior distribution. And then you have various ways to define such a Monte Carlo Markov chain methods. And the most famous one is the Metropolis hastings. So what Eric Moline and Marc Lafiel and others has done is to show that you can actually do that, but by only at each iteration sampling only once, doing one step of Monte Carlo simulation and doing only one step of the Markov chain without waiting for the convergence of the Markov chain and without waiting for having enough samples to have an accurate estimate of the integral. And this, so this scheme has been also further explored by Stephanie, who also showed that the whole thing can converge even with very mild, under very mild conditions. Okay, so I'm sorry for this small parenthesis into the statistical world. The take-home message is that this algorithm allows first to have a real maximum likelihood optimization, and where you really integrate over the hidden variables. And I think that's really in optimization stabilize, I think, the whole optimization. You have a random exploration of the support of the distribution, so it's not like a gradient descent where we always go straight in the direction where you can optimize your cost function. But you explore the neighborhood, which also it's a key factor for stabilizing optimization. And the other thing is that we have theoretical proof of convergence of the whole algorithm, which gives some guarantees of what we're computing. But of course, in the ideal, you have still a lot of things left to the users. Maybe one important thing is the choice of the sampler. So we have a lot of design choices here, choice in terms of the proposal distribution that make the whole algorithm to behave quite differently. And of course, like in any optimization algorithm, you have a lot of parameter setting and initialization of variables and different other parameters that need to be tuned and play, of course, a great role in the optimization. So now we have defined this, I mean, it's quite a generic model and a generic optimization scheme, so we will specify this in two different settings. So the first application would be to model something quite simple, which is just the progression of a single or few biomarkers. So we can look at the most simple, the simplest version of this model in the univariate case. In the univariate case, there is no more what we call space shift, no more exparallelization. You have no space for that in one dimension. So you have one geodesic, which is just one curve in 1D. Okay, and the only thing that's left is the time parameterization of this curve. And if you go even one step further in the simplification, you can assume that your manifold is R, and you have the canonical metric, and at the end, wow, you have a curve which is just a straight line. Not very surprising, but you can play a bit more and see that M is an open interval, and you can like handpick the metric so that you have a geodesic which has the form of a logistic function. We can just come back on this very simple straight line model and compare this with what has been proposed in the biostatistical field so many years ago. So the layered and weird model, the usual model, is a random slope and random intercept effect. So schematically, you have the different individuals, you have the different you have one population average regression line, and you have two random effects, one for the difference in the intercept and one for difference in slope. And you see that intrinsically in this model, you need to have like a common reference time t0 where you can compare values, things that you don't have. And if we rewrite our model in the 1D case, you will notice that you can interpret that in another way. And so we have the different individuals, we have a population average straight line, but what we measure actually is the variability in the time at which each subject crosses a specific values of the biomarkers. So we somehow just flip the role of the x and y axis, the role of the data and the time axis. So we can do that. We can here we have so cognitive scores, which is ADAS-Cog, which is a measure of the cognitive performance of someone. And we do that for a bit more, 1,000 individuals, observed on average 5 times, with a mean of 3 and max of 11. And that's the raw data. So for different individuals, we have this series of observations for a few of them, of course. And so we estimate this univariate model with the logistic curve model. And on the right here, so what you don't see is that all these pieces of curves actually derive from a single geodesic here, which has been just translated along the time axis and adjusted for the pace of progression. And so we are able to reconstruct the different patterns here of progression from a single logistic curve. So each patient here is characterized by 2 parameters, which is the amount of time shift that we have and the adjustment in the pace of progression. So we have two individual factors, so the time shift here and the acceleration factors. So here you have the early onset and there are the late onset individuals. Here you have the slow progressor and the fast progressor. And each point is one individual. Okay, that's a very coarse measurement of the disease severity, but still you can see that in this whole population we had people that were we call stable Alzheimer's disease patients that were diagnosed with the disease from the beginning to the end, and that's the green square, and we see that it tends to be here on the upper left quarter. We had also stable controls, that's people that aged normally, and that tends to be on this quadrant of the diagram. And in the middle, you have people that have intermediate stages. Some of them, what we call converted MCI, mild cognitive impairments, have converted to the Alzheimer's during the observation period. And they tend to be, on the average, more closer to the Alzheimer's disease patient. Of course, this is not very impressive, but at the same time, we have just one single measurement to describe a very complex process. So of course, we don't want to limit ourselves to one measurement, so we can have a series of measurements. And that's quite easy to do. If you to extend 1D manifold into ND manifold, you can just make the product manifold and have the product metric, which at the end makes your population average geodesic to be 1D geodesic on each coordinate. And here we are interested in a specific question, which is what is the specific ordering at which specific events occur during the disease progression. So we make a further assumption that this population average geodesic has this particular form where we replicate the same 1D geodesic, but just shifted in time across the coordinates. And so what we're interested in is this delta factors, which tells you that one coordinate will be in advance or delayed with respect to another coordinate. And then we see that for deriving one subject-specific trajectory, we'll do this X parallelization and this product manifold. And we see here that the effect of the X parallelization is just to add a random perturbation on these delta factors. So it just changes the relative timing across the different coordinates. So it's just illustrated here. So on the 2D case, so here you have the R2, where you have the first coordinate here and the second coordinate there. And here it's another representation, with you have time here and the 2 coordinates there. So if you just focus on the blue curves is a geodesic. So we have two coordinates, which are two logistic curves. And this builds a parametric curve, which looks like this, which reaches the corner 0, 0 to the corner 1, 1. And if you do the X parallelization here, so you end up having here another curve, which is the pink curve here on the 2D plane. And you see the effect of it is that the relative timing between the two coordinates has just changed, but both of them remain parallel. So we can apply this using, the same score as before, but only having an aggregate score. We can subdivide it into different categories for different specific cognitive functions. And so we see that we subdivide it into 4 categories. And so we have the hypercube at the power of 4. And we used this kind of what we call propagation model with the logistic curve model. And here is the average model. So here you have time, age. And this is the 4 different scores. So you have memory, concentration, praxis, and language. And so what you see is that on average in this population, okay, the memory is the first cognitive function that is altered. So the higher the score, the worse it is. And that's not very surprising. Everybody knows that Alzheimer's is started with memory complaints, and then followed by concentration and language and praxis. But what is interesting here is that now we have more quantitative view of the disease progression, at least at the cognitive level. And also, this model is not just a population model, you can personalize it, so it has a variability. Variability that we said in terms of speed of progression here, so we can be a slow progressor, it can be a fast progressor. You have a variability in the time shift, so it can be early onset or late onset individual. And here, because we are in multivariate setting, you have also the different components encoding for the variability in space, which here means the variability in the sequence and timing between the onset of the different symptoms. So here, for instance, you can see that here you have the language, which is altered much before the praxis, and here it's in the other ordering. So you can account for changes in the way the disease progress in different individuals. So to have a more quantitative evaluation of what we do, so we focus on only the people that were not diagnosed with the disease at the beginning of the observation and end up being diagnosed with the disease during the observation period. So for each individual, we have a time here, which is the age at which the individual has been diagnosed really with the disease. So we have here our model that is in some reference timeline, and we estimate here the time here that would correspond in this sequence of events of the time at which people is diagnosed. And then we can map this time to each individual spaces thanks to this time parameterization function. And we could then predict the age at which the person has been diagnosed and measure the error in prediction that we made. And so here is basically focus on the right hand side, that the value of the error that we made in prediction. So we see that the median error here for 0.5% is like at 2.5 years. So which is not accurate enough to be used in clinical practice, but again, just considering only 4 measurements of cognitive function is not too bad. So yeah, we'll skip that. I don't have so much time. So this is the first instance of this generic model that we propose, and now we can go one step further and analyze slightly more complex data, where the data are actually functional values that are distributed at the node of a graph or a network. So here you have different time points. You have an individual. You observe a graph where at each graph you have different values of, let's say, a measurement, like the cortical thickness, if it rings a bell in your mind. So what we propose is to use still a product manifold, where now the product is much, much higher dimensional. It corresponds to the number of nodes that is in the graph. And we do not assume anymore that we have the same type of profile at the different coordinates. So we have a generic form at each node. We have a generic curve, which is the 1D geodesic in a 1D manifold, and which is typically parameterized by two parameters, like, for instance, a point and a velocity. So, of course, it's way too many parameters to estimate, and we want also to impose some regularity, because we assume that the patterns of propagation we want to see across the nodes have some spatial regularity. So for doing so, we impose that any of these parameters, like the P or the V's here at different nodes, are actually a sample of this distribution, where we pick some evenly spaced control nodes on this graph, a very small number of them, and we interpolate weights on this at these specific nodes to give the value at all the other nodes. Where here the distance here is the distance, the geodesic distance on the graph this time. So for instance, if surface mesh, this is really the distance between 2 points on this surface. And so this has two consequences. First, as I said, it encodes some regularity constraint on the parameters that we estimate. And second, it allows a drastic dimension reduction. So we can do this to see the typical spatiotemporal profile of atrophy of the cortex during disease progression. So again, you have age here. This is maps of the cortical thickness at the different ages in the mean average scenario of disease progression. So we see that the value here, for instance, in this region here is decreased quite a lot during disease progression, and this is not surprising because this region is very close to the hippocampus, which is a structure which plays a great role in memory. And we see that other regions that decrease quite well are these in the temporal or in the frontal lobe, which is quite in line with the medical knowledge. And we see, for instance, this area here near the central cortex here, which is thin at the beginning and remains thin, quite stable along the disease progression, and that's a pretty good thing because this region is a motor area, and Alzheimer is not known to develop motor symptoms. And again, so when you show this to a clinician, okay, he retrieves some of his previous knowledge, so it gives us confidence in what we estimated. But the main interest is not to just display this average, but again, to see how you can adjust this model to individual cases. So here we evaluate the ability of the model to reconstruct maps of cortical thickness that you see in individuals. So here you have two different cases. They look the same, but actually they are quite different. If you look at the color map here, the values, the range of values here are very different for the two of them. And we see that adjusting on the left-hand side, you have the prediction of the model, and the right-hand side, you have the true, no, that's the reverse. This is a true value, and this is a value predicted by the model. So if you look carefully, you see that we can average, we can reconstruct the observation quite well. At the same time, there are some details that we missed, and especially we have here more regular patterns. If you see here, it's difficult to see with the projecting system, but this is much smoother than this one. And so, of course, we can quantify all the errors across all the observations. So on this, so we have 1.5 million of surface patches from the different meshes, from the different individuals, and at the end, so that's the histogram of the errors, and that's the distribution, and you see that the most errors are here in this very specific part, which is close to the boundary, so it doesn't play a very great role. And again, we can see the distribution of the dynamic parameters, so we account for variability in the pace of disease progression or time shift here. And we see the histogram for 3 different subgroups in this population with genetic factors. And so this is the more alleles of this APOE4 genes, the more at risk you are to develop Alzheimer's. And we see that on average, this green histogram tends to be more faster progressor and more early onset than those having no alleles of this particular gene. And that, again, is quite in line with the medical literature. Okay, so that's more or less as far as we can go here in that direction, because in this specific manifold there are, two characteristics. You know exactly the geodesic in closed form, and you know the parallel transport in closed form. So the whole model can be estimated quite easily because you have the closed form expression for nearly every piece of the model. If you look at for different manifold, usually you don't know how to compute geodesic, and you don't know how to compute parallel transport, which is the big thing here. And so we here develop a new numerical scheme for defining computing parallel transport along geodesics and manifold. Because if you want to compute parallel transport in numerical fashion, you have not so many choices. You can choose to integrate the definition of the parallel transport with a covariant derivative here, but then you need to compute the Christoffel symbols, and when you are in very high dimension, this does not scale up. You can use the Shields ladder, and Xavier here have developed this scheme in the past, but this requires to compute the Riemannian exponential and exponential logarithm. And computing the exponential logarithm is usually very difficult and relies on another optimization scheme. So you make an error at each step, but you don't control for controlling the overall error of the scheme. In particular in our cases. And so an idea that had been around for a while, and notably in the work of Laurent Younes, has been to use a Jacobi field to approximate parallel transport along geodesic. So if you want to parallel transport this vector W along the base geodesic here, you can define the Jacobi field in this direction W. And if you don't go too far, for small h here, the derivative of the Jacobi field here is a good approximate of this parallel transport. So our job were to borrow this idea and to say, okay, what is really the minimum number of operations I can make to have convergence of this scheme? And it ends up that we can really be very coarse in the way you can do that. So you have a point, a velocity, and a vector v, w. So you can compute so along a small step h, you approximate the geodesic with only a scheme of order 2. So typically a Runge-Kutta scheme of order 2 only, that's enough. And to approximate the derivative of the Jacobi field, you just need one other geodesic. So you make one perturbation of W in the direction with a small step epsilon, and you just make in a local chart a difference between these two coordinates. And you take this as the approximation of the parallel transport once it is rescaled. And if you do that, we showed that if you repeat this n times, at the end for h equal 1 over n, you end up with a linear convergence rate. And this linear convergence rate is the same as the Shields ladder. So we can compute the error for the spheres and the symmetric positive definite matrices with affine invariant metric. And to see in closed form, you have the true expression. You can measure really the true error. So you see that the scheme always converges to 0 in a linear fashion, which is in line with what we proved. And you also have different setting. You can increase the order of the Runge-Kutta, and that you see that it increased, but not so much. Or you can increase the number of different schemes that you can do in the parallelization. Here you have only one epsilon, but you can make just another perturbed geodesic and make a second order scheme, finite difference scheme here. And that tends to be to have a great effect in optimizing the rate of convergence, but at the cost that you need to compute one more geodesic. So you increase the number of computation you have to make at each step. And of course, we compare this with the Shields ladder and the sphere. So here you have the convergence of the Shields ladder, and here of our fanning scheme. So both are linear convergence, and on the specific example, you have a constant which is slightly better here. So once you have this numerical scheme embedded into the model, you can address quite more challenging application, which here is more in shape spaces, in deformable shape spaces that Alain and Xavier have told about yesterday. So I won't be too long, but still, so I'm not sure, Alain, if you presented this specific equation. So the way we built a diffeomorphism of the space is to integrate a time-varying velocity field here. And so what we propose is to have a velocity field which has very specific form, which is an interpolation of specific momentum here, which is the yellow arrows here, at specific control point C here. So that's basically what we call the state of the system, the set of control points and momentum vector attached to them. And of course, if you have two endpoints on this set of control points and momentum vectors, there is an infinite number of ways that you can reach a specific state from another one. And among all of them, we choose the one that extremal pass of this energy function, which is the integral of the velocity along the curve. And very classically, you have an Hamiltonian set of equations which tells you along this geodesic how control points and momentum need to evolve. So we can write this simply as, so we have a state of the system which follows some Hamiltonian system of equation. If you have that, you have completely, given the initial condition, you have completely specified the driving velocity field, and that you can integrate any point in space to have the trajectory of any points along the flow of diffeomorphisms. So that's one instance. You see the control points into the momenta. They are evolving according to this Hamiltonian system. And you see the mesh, the surface meshes here that are just deformed according to this flow of deformation. So if you see now all the diffeomorphisms that you can reach for a specific initial value of the control points and specific initial value of the momentum, that satisfies all these constraints. You have this G here now is a Riemannian manifold. So classically, what in the work that's been developed mostly by Alain, Michael Miller, and many collaborators, you have no constraint here on the structure of the velocity field. You just assume it to be in a reproducible kernel Hilbert space. In that case, G is more behave like an infinite dimensional Lie group. And by here restricting this V to be in a finite dimensional subset of the RKHS makes this G now a Riemannian manifold, which is much more convenient to include them into our statistical modeling. And so at each point along the geodesic, the tangent space here is so a finite dimensional subspace of this V. And the metric is given by this matrix, which is the kernel with all different pairs of control points. So we can derive now exactly the same similar statistical model that we have done before, just need some slight adjustment. So this geodesic here is nothing but a geodesic flow of diffeomorphism. And the initial point here is now fixed to be the identity mapping. And you have on this tangent space control point C0 and alpha momentum vector alpha 0. The X parallelization here to get this diffeomorphism at this point here is nothing but the combination of two diffeomorphisms, one which reach the point here and another one in the direction of the parallel transport of these vectors, which can be computed by integrating twice the Hamiltonian equations. And now what plays the role of this P0, which is no more a P0, which is the identity here, is the template shape here. So your observations are shapes. And you want to estimate a mean shape here such that your observation is a diffeomorphic transformation of this template shape. And this diffeomorphic deformation, as you said, is the result of one exponentiation and a time of parameterization function. So it's a bit abstract. So we want to see, for instance, what is this X parallelization doing on a real shape. So here you have, look at the first line. The first line is a geodesic in the shape space. It is encoded basically by just this blue arrow, blue momentum here, which creates this driving velocity field here in blue. So what does a geodesic is just to raise the hand of the man. Now on this shape we have red arrows. Red arrows define another velocity field and another deformation of this shape into this shape on the bottom here. Okay, so the leg has moved here slightly bit in this direction, hands has been done here. And now we can parallel transport this red velocity field along this geodesic curve. And so you see here that the position of the control points and the momentum are adjusted with the motion along the geodesic. So here, for instance, this motion here now is displaced from time point to time point. And now given the rate velocity field here, we can just exponentiate it to give the deformation of a shape from this one. And at the end, what we have is a series of observations here, which builds the X parallel curve in the shape space of the curve on the top. So now we run the whole longitudinal model. So we simulate different individual trajectories, which we sample 5 time points on each of these 20 individual trajectories. We run the whole estimation program. And at the end, what we have is that was the true value of the template shape, the true value of the velocity field. And that's what we have estimated by the model, given 20 individuals observe 5 time points each, which is pretty small data set compared to the size of the dimension of the manifold here that we are considering. And here there's a difference between the two. And here the magnitude, the difference between the two here has been magnified by a factor 10 to be able to see it. And here you have the behavior of the algorithm across the iteration. So we see that the variance explained very quickly stabilized. Like for other factors like this, here the variance, some variance parameters just very, very quickly stabilized. And other parameters, it's much more difficult to have stable estimates. And again here, so given just the average model that we have, we can reconstruct the trajectories of any individual data set. And here that's how the model can, you can see very accurately, can reconstruct the prescribed individual trajectories. And we can do that, exactly the same thing on the shape of the hippocampus. So this structure, which is extracted from the magnetic resonance imaging, and that is, I mean, has been very, very well observed in the literature. And so, but usually, I mean, the clinical literature is just been summarized by the volume of the hippocampus, and you see if the treatment can or not alter the rate of decrease of this volume. And here we are able to reconstruct not just the curve of a volume, but just really how the shape is evolving during disease progression. And you see clearly that the atrophy of this structure is clearly not isotropic, but has a very specific spatiotemporal patterns. And here we correlate here the age of diagnosis with respect to this time shift, individual time shift variable. So we see that the model captured well the pace of disease progression across individuals. But of course, for here only 20 individuals, it's not possible to decide about statistical significance. So just to summarize what we have done, so we have first proposed a new mixed effect model for manifold valued data and longitudinal data, which makes two important concepts. The concept of X parallelization to model the difference in the individual trajectories, and the concept of time warp, which encode the difference in the dynamic, in the pace of which the individual follows the trajectories. And this is a mixed effect, so it's important to have average, but also to see how we can personalize this average model to individuals. So we also developed this Jacobi's fan scheme for parallel transport, which can be converged using very, very few a number of computation, which is key for the implementation of this model for more generic manifold. And then we construct these personalizable models for different kind of data. So you have cognitive function, alteration of cognitive function. You have change in the cortical thickness measurements, which is measurements distributed on a fixed graph, or you have the difference in the shape of the graph across time. And we also start evaluating the predictive power of the model to be able to predict, for instance, the age to disease onset. And of course, there is here much more work to do in that direction than what we have presented, which is just prediction by model personalization. I would like to finish by to thank all the person who have contributed to this work, and there are quite a number of them, so our PhD students and postdocs, software engineers for all the implementation and experimentation. I will mention the two important collaborators that has greatly impacted the development of this work, so Stéphanie Lassonnière and Benjamin Charlier, and of course the whole Aramis lab and our funding sources. Thank you for your attention.
Questions?
In the time evolution of the shape, could we imagine that you assume that you have only one mean path, or you could have different categories? So you have a multimodal statistic on different class of Alzheimer disease. So you have to cluster first before averaging? Or?
Yeah, absolutely, you're right. Assuming you have one single mean for the whole population, which is as diverse as Alzheimer's, this patient is not ideal, clearly. And you have surely multiple modes in this distribution. So there are different strategies. So one is to add one more layer in the hierarchy. So you assume you have class variables, and then you derive one model for different classes. But that started to be explored by Stéphanie, and that's very challenging in optimization because you mixed discrete variables with very continuous models, and makes that you can be easily trapped. I mean, the cost for changing a misclassified observation to another class is very high and occurs very rarely, too rarely. So to find the good optimization scheme to deal with that is still, I think, quite an open problem. You can also say that at the first stage you estimate one single mean, but then you have all the individual parameters, and you can look at the posterior distribution of these individual parameters and see if there are bimodal shapes, and then you can think of pragmatic strategies to just divide your set of observation to the different modes and to re-estimate parameters. So yeah, there is large avenues for working on that.
So I have another question, which is, so the x-parallel curves. So obviously I would like to have the same thing for surfaces, but we already discussed, and it's not so easy to do. But I was just wondering, I'm expecting, like on the sphere, even if you start with a great circle, and at some point you're gonna reach the end of the sphere, so it means that even in simple manifold, you're gonna reach some singularities. So when you do that with DFOs, did you try to push the machine to see these discontinuities appearing? What type of, is it far away? Is it, what's your experience on that?
So as you might have noticed, the experience in DFOs are the latest one. So the one we have less time to explore. So definitely I could not have not experienced that so far. We have, at the moment, too many problems to solve on the optimization scheme, stabilization of the parameter estimation to push the model towards the limit. My general comment would be that statistics on manifold is nice because it encodes the smoothness property and the structure that you have in the data. But I strongly believe that if the variance of your data is too large, then you have, I think you have to accommodate your model. Either you estimate different models at different locations, or you do your barycentric subspace division, or, definitely you cannot estimate one model and with very large variance on the manifold. For me, it does not seem to be very sensible.
Okay. Other questions?